All right. Hey guys, welcome to another episode of Robo Papers. Really happy today to have Guangqi, one of the co-authors of this paper called GSWorld, Closed Loop Photorealistic Simulation Suite for Robotic Manipulation. Thank you so much for coming, Guangqi. Maybe as a start, if you can share a little bit about yourself.
Yeah, sure. Hi, nice to meet you, Chris and Michael. My name is Guangqi. I'm a master's student from UC San Diego. Currently, I'm working with Professor Xiaolong Wang, and today I'm going to share the paper called GSWorld. It's really nice to meet you guys.
Yeah, likewise. Thank you so much for making the time. I guess you can dive in. Yep.
So, GSWorld is a real to sim to real paper. So let me introduce the title first. The full title is called Closed Loop Photorealistic Simulation Suite for Robotic Manipulation. And this work is a collaboration between UC San Diego, UC Los Angeles, and the Meta Reality Lab. To summary, GSWorld is a photorealistic simulator which combines the current state-of-the-art 3D reconstruction method, which is the 3D Gaussian splatting, with physics engines, which in our setting is the many-scale simulator. And we apply the photorealistic simulation to various downstream applications, including the zero-shot sim-to-real, pixel-to-action policy learning, and the data aggregation method for sample-efficient policy learning. And we also do the reproducible benchmarking, which is that we can show the correlation between the simulation evaluation and our real-world evaluation. And they have a high correlation. So we can use the simulation evaluator as a proxy for the real-world evaluation, which is very expensive. And we also do the virtual teleoperation. We can immerse into the simulation world. We can use, in our setting, we use the keyboard and mouse to collect data set with a humanoid robot here. And finally, we show the GSWorld can bridge the sim-to-real visual reinforcement learning gap by doing experiments with soft abstract algorithm and deploy them on the real world. So I guess for let's just have a quick view of the generated data set. You can see that this is the task from Franca Research 3, which is a single-arm tabletop roll arm with Umi gripper here. And for each task, we use motion planning to collect data. As you can see here, we do 4 experiments, 4 tasks on the Franca platform. And all
this
of
is a very
them
nice looking simulation, by the way. A very realistic looking simulation.
Yeah. And next, we show the data collected by the X-arm robot. It's a sit-off tabletop arm. And slightly different from the Franca robot, the gripper for X-arm includes some articulations. For the Franca Umi gripper, it's just parallel and has 1 degree of freedom. But for the U-factory gripper, which is mounted to the X-arm, as you can see here, it has some articulated joints, revolute joints. And we do 3 tasks on the X-arm platform. So we see the data collected by GSWorld, which we use photorealistic rendering from 3D.js to create a data set. And we do zero-shot sim-to-real image learning to transfer the policy to the real world. In this part,
can I ask about something we were just looking at? Sorry, this is gonna bother me. There's the tidy table one. I mean, all the rendering on all the models look great, but the gripper isn't fully closing around the spoon there, right? Is that just the shape of the gripper where the internal pads are pinching, or is it something else?
Yeah, it's a really good question. I would say that it's a very detailed observation. I guess you want to ask about the wrist cameras here, right?
Yeah, they're on the right side.
Same thing for
we find
banana,
this problem. Yeah. We find this problem is because that the meshes, especially the collision meshes for the objects, is a little bit larger than its visual meshes. So in the simulation, the fingers and the objects have collisions, but they from the visual rendering, they are not contacting with each other, and this is a problem. Yeah, it's the same. If we look at the rendering from the physics simulator material, we can see that the gripper and the object, especially when the object is seen, there is a space between the gripper and the objects. Yeah, I think this will introduce some kind of visual gap, but currently there's no perfect solution for this problem.
I guess it turns out not to matter much, or I guess we'll get into it. So okay.
Yeah.
Yeah, we can move on.
Okay, so given the data set is very photorealistic, it looks almost the same from the real-world teleoperated data set. And we can use this data set to directly train a policy and deploy them in the real world in a zero-shot way. And here's the experiment with zero-shot symmetry imitation learning. In this case, we trained the action chunking transformer algorithm with purely simulated data set, and we deploy the policy into the real world zero shot. Here's the result. We can see that all of the 4 policies successfully finishes the manipulation tasks. And another way we want to start from simulation is that in simulation we have a lot of privileged information to use, and this information is absent in the real world. So we want to do some more fancy learning algorithms. So we want to say that if we can, in the current robot learning pipeline, we identifying the problem and we designing method, then we collect data set, and we do the policy learning and finally deploy the robot policies. But after the policy deployment, the policy cannot easily be improved anymore. So we want to ask the question: can we make the policy robot policy learning a closed loop? Like, can we use the results or the feedbacks from the deployment to still improve the policy learning? And here is our closed loop data results. The idea is quite simple. We do data collection in each data iteration. And in each iteration, we collect 100 demonstrations with motion planning, and we do the policy learning and policy deployment. And in this deployment process, we record the failure cases of the previous policies. And in the next iteration, we start from these failure cases. We start from the failure cases where the scene is not disrupted. So we can start from this point and use motion planning to tell the robot, you failed this case, and if you see this observation, you should follow our new instructions here. This is to correct your previous failures. So the robot can learn from some kind of mistake correction. And we show that this kind of data learning is more data efficient than learning from scratch. We compare the data result with learning from scratch, which is we blindly collect 500 demonstrations, since we use 5 iterations in our data learning. And we separate the data set into like 100 demonstrations, 200, 300, and 400, and 500. And we run 5 policy learning, and we deploy them in the real world. And compared to learning from scratch, data is more sample efficient. Both the data requirement and the policy performance is superior to learning from scratch. So here's the result on the frontal robot. The videos to the left is our data results, and the videos to the right is learning from scratch. And we show the results after 5 iterations, which means both of the policy trained on 500 demonstrations.
So for your dagger part, you basically do the corrective actions within in your simulation, right? The release GSWorld, right?
Yeah, we just since we can know where the robot fails. For example, if the robot successfully picks up the first can, or if it fails to pick up the second can.
Mhm.
Given this information, we can reset the scene to before the robot fails. And start from that point, we collect more data. And we want to see that this data set collected by Dagger is better than we just from the start point and doing doing randomization, object randomizations, and motion planning to get the same amount of demonstrations. So Dagger is more data efficient. I also have more experiments here.
I'm curious, like, so how do you get the real to sim part? Like, how do you capture to get this into many scale and bring the realistic rendering so called? What are the inputs?
I see. That's a very core problem. Sorry, great question. In our part, we first do the 3D training, and we take photos around this thing. And as you can see, we have a specially designed is that use the Aruko tag to build a metric scale scene, which means the 3D reconstruct scene has the same scale with the real world. The 10 centimeter in the simulated scene is exactly 10 centimeters in the real world. And we do the code map to get a point initialization for the 3D.js. And then we do the vanilla 3D.js training to get a PLY model, which is exactly the digital twin of the real world scene. And we want to, in the next step, we want to align the simulation with the real world. We use some point registration. In our case, is the ICB algorithm. And we align the simulation points with the real world points. So we know in the 3D.js points, which one is belong to which part of the robot. And in simulation, we can get the CC poses of each part of the robot, and we will do rigid body transformation to the Gaussian splatting points. And in this case, the point is starting to moving, like you see in our teaser video. The whole thing is moving as well as the objects. So the key takeaway is we have a label to assign to the Gaussian splatting points, and we will see which part of the point is belongs to, like the objects or which link of the robot arms.
How do you think like scalable the real to sim part will be? I mean, obviously this is a academic paper, so you can do it like so. Because if you can do this like in a scalable way, then it's extremely useful, I imagine. Like you can do all this like closed loop stuff. But it seems to me the real to sim part is non-trivial. What do you think, Guangqi?
I would say that to reconstruct a scene well, definitely takes a lot of labels, and so our choice is like making the reconstruction as scalable as possible. Where we just since the tabletop scene is comes with a fixed base robot arm, so we reconstruct the arm and the whole scene together, and then we do the object reconstruction in a separate way. So we can add different objects to the static scene, and compared to some other method which directly reconstruct the object and the whole thing, and then do some Gaussian editing or in painting. I think this way is more easy for us to combine the objects and the whole thing together. So it's comparatively more scalable. And I would agree that to reconstruct a scene well really takes a lot of efforts. That's true.
So can I ask just to follow up? So we're talking about the main issue is all these labels and segmentations and so on. So it's November 20th as of this recording. Yesterday, SAM 3 was released. Do you think there are AI tools like this that will make it a lot easier to do this?
Yeah, I think SAM 2, SAM 3, SAM 3D is very promising. I think it has huge potential to be integrated into the current real-to-sim pipeline. And the most exciting one, I would say that is its feature to generate a lot of 3D assets. And, for doing real-to-sim to real, the object has to come with the 3D assets. Otherwise, we don't know the shape in the simulation. So I think the most helpful point for the SAM 3D is to generate 3D assets, and these assets can be used in the simulation. And compared to our choice is that we choose objects from the meta dataset, which is the digital twin catalog and the YCB dataset. If we want to do the learning with a custom object, we want to first have its 3D assets. The SAM, the newly released SAM, perfectly help us in this way.
Yeah. Sorry to interject. Maybe you can go back to where you were just now, the closed loop thing, I think.
Okay.
Yep. Mm-hmm.
Yeah. So the closed learning on the Franca platform is purely sim to real. We just start from policies in the simulation, and we want to next we want to answer a question is that if we can improve a real world policy, let's say we have some data collected and we train a real world policy, can we use the GSWorld to improve the real world policy? So we also did this experiment, and this time it's a real to sim to real data aggregation learning. Instead of starting from some randomly initialized policy, we put a real world policy in the GSWorld, and starting from the rollout results from the real world policy. So we can in this way improve the real world policy by doing data in the simulation, and we deploy it back to the real world, and we can see some performance upgrade here.
Yeah, in fact, your papers have some charts. I don't know whether this is a good time to show like the improvement on the success rate. If you want to switch the paper, I saw some like how the success rate basically improve as you have. So could you talk us through some of these charts, like what's going on here?
Yeah, this is exactly the results between those videos. And I would first introduce the sim to real closed loop data training. We can see that the yellow lines indicates the data learning, and the blue lines indicates training from scratch. And solid lines means solid line means we deploy the final policy into the real world, and the other one means we deploy the policy in the simulation. So we separate the data learning into 5 iterations, and we collect the demonstrations in each iteration. So the total number of demonstrations is 500. And we can see that the overall trend of the data learning is to improve the policy performance in all our settings with the increase of iterations. And we can see that to compare the real-world performance, we will see these two lines, these two solid lines. And we will see the data is consistently outperforming the training from scratch method. And this is true across all the 4 tasks on the Franca platform. And this is the results shown by the previous videos. And the dashed lines here is to verify the visual benchmarking result, which is that we show the strong correlation between the simulation evaluation and the real-world evaluation success rate. So they are also put on this feeder to show the benchmarking result. And another one is the real to sim to real data. In this experiment setting, we aim to answer the question that can we improve a real-world policy by reconstructing the real-world scene? So the answer is definitely yes. And we use the data here to improve the real-world policy. And in the first iteration, the success rate is the policy trained with several real-world demonstrations and in the simulation, and we do the data learning, and we record the performance of each iterations here. And this result is similar to the sim-to-real learning. The policy performance consistently increase as the number of demonstration increases.
Got it. Yeah, I guess so. The takeaway seems to me is that basically intuitively Dagger should move the needle. It's just that whether you do it in the real world or you do it in sim. Obviously, sim you don't actually break things, and so as you okay, and so the actual it's just a lot more operationally easier to do it in sim, but it transfers.
Yeah,
Okay,
exactly.
cool, got it. Mm.
Yeah, so in the real world, the real trouble is that it's not very safe, and the second is we want to restore the scene to exactly the same before the policy fails, which is not trivial in the real world, because we have to record the object poses. We may introduce some object tracking method here. So in simulation, everything is easy. We will get the CC pose of all the objects, and we know where they were before the policy fails.
Got it. And I guess you maybe you haven't talked about this yet. The visual benchmarking, I think, is quite interesting as well.
Oh, since we are already on this page, I will briefly talk about this chart, and we'll go back to the website to see some video demos. So visual benchmarking, personally, I think is a very useful way to do the policy evaluation. Since previously commonly we will evaluate the policy in the real world, which is very expensive and which also takes a lot of efforts. But in the simulation, the evaluation is very cheap, and we can do many trials, which makes the result more convincing and robust. So the core problem here is that the evaluation result really indicate something? Does it means does better simulation evaluation performance means better real world evaluation performance? So in this way, we want to know, is there a proxy for our real world evaluation? And we have to have a digital twin, which is exactly we digitalize the real world thing, so we can know the performance is correlated between this simulation and this real world, and our experiment results verifies our claim. We can see that in this figure, the y-axis shows the simulation success rate, while the x-axis shows the real-world policy evaluation. And for the same model, the success rate between the simulation and the real world is correlated. And for various models, like all the squares and the dots here, we will show the correlation between the sim and real evaluation. And better simulation models indicate better real-world models, and vice versa. And let's go back to our website.
Actually, I just want to make a casual observation there. I wonder if you have any thoughts about it. It seems to me that the simulator seems to underestimate how good pi it is in the real world versus like ACT it overestimate.
Yeah.
Why do you think? Do you have any intuition why like it overestimate for some model and then underestimate for some model?
Oh yeah, that's an insightful question and very careful observation. I think the most obvious reason is that for pi zero training, the real world, we only use real world data. The squares the scrolls data here is pi 0 trained with real-world data set. So if we want to deploy the real-world policy into the simulation, there will be some kind of performance downgrade. And contrarily, for like ACT, we do many simulation policy training. And this kind of training will tend to perform better in the simulation environment. And they will perform like not so good in the real world deployment. So maybe for the ACT, since we have a lot of models trained with simulation data, so in the real world, the success rate will be slightly lower. Yeah.
I think this is still useful regardless. I mean, if you know that the policy is just trained from more real world data, so when you evaluate in GSWorld, you can still trust the correlation. It's just that maybe you can add another, 10% of success rate. You can assume maybe roughly. If it's a model like Pi.
Yeah. The benchmarking is very useful, especially when you want to do some policy architecture exploration and want to see which kind of policy architecture is better. And in this case, instead of just want to deploy maybe hundreds policy in the real world, we want to do it in the simulation, which is super cheap here.
Got it. Cool. Yeah. Sorry. Yeah. Cool. Thank you.
So let's see some real world demos here. So here's the results that we exactly talked about in the paper, which is the visual benchmarking.
Can you explain what we're seeing here a little bit? So we've got like this little table, a wooden table on the left side. You've got these Melissa and Doug toy cans. There's an April tag for some reason, and on the right there's like a funny face for the thing. Like, what's the story behind this setup?
You mean why we choose a scene like this, or why we choose
exactly? Like why change this? Why this scene? Yeah. What's it showing us?
Interestingly, you may notice that for the Franca and the Epsilon, we choose the same tablecloth, except that one is white and one is black. And there's really some stories behind the tablecloth choosing. Since we choose this because these two tablecloths come with a lot of features, and it's easy for CoMap to do the feature map. And we choose clothes with like repetitive patterns or with some plain color. The CoMap mapping for Gaussian splicing training will be much harder. So also this works for the camera calibration, since we are using the CoMap to do the camera calibration, and we requires very good feature mapping. And for these objects, I think we choose this is I bought this snap bots from the Target, and we just find it's very cute. And it also the key point is that the bots is also with many visual features, especially the other side, but we don't use the other side. Also, it's easier for the sim to reconstruct its 3D mesh, so we choose this one. And for this thread itself, we want to we want to use some different objects, and we think maybe this spice rack is more close to the real world kitchen settings, and so we bought this rack to the left side. And this page is showing that the visual benchmarking results, and in the top is the real world evaluations, and in the bottom is the simulation rollout of the same policy. And we will see that they show a similar task compilation here.
Cool. Okay, so that makes sense. So the bright textures and shapes and all are CoMap, so they make it easier for you to create the meshes.
Yeah, exactly.
But we see that there's this yellow mustard bottle which doesn't have a ton of texture, and that's okay. Is that just because it's an unusual shape? It tends to work well. Okay.
Yeah.
Cool.
Yeah, and we also have the benchmarking for the Pi Zero policy.
One other question. Sorry for so many questions here. I did note, like, the other thing you notice watching these videos is that the mass in the simulation, the mustard bottle's empty, or right, like the mass is much lower than in the real world. Is there have you put any thought into that? Like
the real world, like the bottle is also empty.
Oh, it is. Okay.
This
It just
bottle is
feels
also
different.
empty.
Okay.
Yeah, this one now also. I would say that we did not do much efforts in bridging the simulation and real world physics gap, but
Makes sense.
it's still quite important.
Yeah, actually, I was just gonna point yet. So like I think this real to sim to real is very visual based. Um, but then obviously the real world like texture do matter, like the weight of the thing do matter. So something could like look quite small and yet be super heavy. Something could look very big,
Yeah.
but actually it's empty inside. And then obviously this in the real world it matters. Do you think it's a fundamental limitation with this kind of pipeline? If it's I don't even know if there's a way to solve it with
You mean
scaling or like
the-
even like a better SAM3 or SAM4, things like that. Because fundamentally, you don't get those.
Yeah.
The only thing information you get is maybe better and better visual, maybe 3D segmentation, that sort of stuff. But you don't get other physical information, and that some of this could be
Yeah.
quite important, I guess.
Yeah, this is a very good question. I think people currently are more focusing on the visual reconstruction, and for some physical parameters, a lot of them are neglected. So we do have some ongoing projects which aims to bridge the physics gap. Yeah, so personally, I think that the physics parameter in the simulation are not exactly the same with physics in the real world, or we would say that for a simulation, the mass is uniformly distributed, but for the real world, it's not. So this is I think this a fundamental problem which requires us to solve. And based on my understanding, the current pipeline people are using is to some maybe manually adjust the physical parameters and to see if it has similar behaviors between the simulation and the real world.
You could also
Yeah,
probably
also
just randomize
for
it, right? Randomize. them.
yeah. Randomization is another good way.
It's take a lot
Yeah.
longer to train, but that's okay.
Yeah.
So that's maybe not okay for a research
as
paper.
itself have. That's true.
Yeah.
Got it.
And also we find some control parameters of the simulation and the real world show some different behaviors. Also for the friction of the gripper or the force limit for the gripper also make a difference. Yeah. So let's move on to another robot we use. Yeah, it's very interesting. We use a mobile humanoid robot here, but we just do some kind of virtual teleoperation. We do not run policy on this robot since our hardware has some issues, and we want to show that GSWorld also can incorporate robots with more complex links and joints here, and this is kind of some random movement. And yeah, have any questions here?
Sorry, actually, so like, so this is in GSWorld, right? So this is in simulation, but
Yeah, it's in simulation.
it's transfer to simulation because you guys take a bunch of photos in your lab and then including the cone over there, and this basically
Yeah.
translated into your GSWorld. I'm curious,
Yeah,
like for example, if you move this virtual robot to near the chair, would the chair behind behave like a normal chair, you think?
Do we include any kind of interactions between the robot and the chair?
Yeah, so right now, is it like a static a Gaussian splat? Like for example, there are a couple of office chairs at the back. Obviously,
yeah.
those are on rollers. So in theory, in the real world, you push it will roll around.
Yeah,
but in this
exactly.
case, I suppose they're static.
Yeah,
Right?
it's static. Just the background. You can view it as a static RGB image.
Got it. So even for this cone, it's like you can't move it. It's like
we
a
didn't
fixed
reconstruct
obstacle.
the
Got it.
cone here. So I think this includes some kind of more advanced digitalization of the real world. We want to transfer the whole thing to the simulation. It's not that easy. And I know some startups, maybe like the Light Wheel, is trying to build as many 3D assets as possible, and in this case, we also want to have the physical parameters for these columns or these shelves, and also the collision and the visual meshes. So it's too complicated, and we only treat the everything here as a background and the robot here as a foreground. And for the robot, we do the segmentation. We assign the labels to each point of the robot, and in this way, the robot can move with the simulation. Yeah, and here, here's another experiment we do with zero-shot sim-to-real visual reinforcement learning. I think this is quite an exciting result for me, because we spent some time modifying the Gaussian splatting in the simulation to make it to be parallel, so we can build many environments at the same time and train the reinforcement learning algorithm. But still, it's not that the frame per second is not that high, so we choose some sample efficient algorithm like the SAC here, and we train the policy with and without GSWorld, which is photorealistic rendering. And we find that with GSWorld, the policy training simulation can zero-shot transfer to the real world, just like previously we have seen in the imitation learning setting. And for reinforcement learning, it is similar here. Yeah, I think we have two tests here to show that GSWorld helps sim-to-real visual IO transferring.
Yeah, I imagine
I mean, for reinforcement learning, the agent training is very dangerous, and the hardware is easy to break. And sim-to-real is a safe way.
Yeah, I was gonna say once you have a simulation where you can do RL however you want, you have privileged information. It's the best.
Yeah.
The question is always the sim-to-real gap. Yeah. Got it. Cool. Yeah, so I guess...
And you don't even need to do any domain randomization or anything to get this to work. It's just like your simulation is good enough that it just works. That's great. Yeah, very nice. Yeah.
Oh, we find that since we are building the scene, taking photos with mobile phones, and the scene is not quite large, so we, in the sim-to-real visual IO, we do not include the views from this wrist camera. We just use a third-person camera which is mounted to the side of the table. And we find that this reduce the sim-to-real visual gap, since for the wrist camera during the IO exploration, it might see many out of domain views, and this gets some.
Okay. It's because of all the background, basically.
Gap.
Yeah. So you could domain randomize the background and then it would work, maybe. Okay.
Yeah.
Cool.
Limited randomizations is used.
Okay.
I think we only use the color jittering, and we mainly because we found that if we use too many domain randomizations, the IO training is not that stable, and this will increase the time we take to train the IO agent. And we also find that.
Sorry, how long does it take to train the agent?
Yeah, it takes approximately maybe over 10 hours. With I think it's 10. I didn't quite remember the steps or the frames, but it takes 10 to 20 hours. Yeah, we use a single 4090 GPU to train the IO agent. Yeah, also we find that with only some color jittering, the policy can already work in the real world.
Great.
Yeah, I guess maybe, since we're wrapping up things up here, Guangqi, what would you say I guess maybe you already mentioned some of these maybe perhaps limitations. Like what would be some follow-up work that you would love to explore to kind of double down on this trajectory you have using this route to sim-to-real?
Yeah, that's a very good question. I think YouTube's really provide many insights into the improvement of the GSWorld. Based on our resources, we would like to say that And direct way is to apply the GSWorld to more dexterous manipulation settings. Currently, we only include the parallel grippers, which is simpler, and we want to see how well GSWorld performs on high degree of freedom hands, and this includes many more revolute joints and many more small links, and this is still like under exploration. And as you two mentioned before, the physics gap is still a problem. It looks like that in simulation the bottle is empty, but in real world it's not. So we have some papers in submission to narrow down the sim-to-real physics gap, and since the GSWorld is the physics relies on the simulation physics, and as long as we have the 60 poses of the simulation objects, we can use GSWorld to transfer the 3D Gaussian points to that objects. So the problem turns to improve the mesh physics parameters.
I suppose like besides increasing the, let's say, degree of freedom of let's say you use a robotic hands instead of gripper, I suppose the objects themselves can also be incredibly hard to simulate, like deformable, like a piece of cloth.
Oh yeah. We're also doing research into deformable object reconstruction. That's very promising. And I think for rigid body and for some deformable objects, they aim to answer different questions. Maybe for the rigid body, we want to do some more fundamental work or answer some more universal problems like the physics gap or still the visual gap. But for deformable objects, we want to first see if the reconstruction works on the deformable objects. And for some manipulation tasks, deformable objects is not that hard to, for example, pick up or grasp. And we want to see that if deformable reconstruction looks real, just like we manipulate some real-world deformable objects.
Got it. Yeah. It seems to me there's a big trade-off here. It's like the reality is hard to scale. You can't break things in real world. So the simulation world seems very appealing in that regard. But then at the same time, it's huge amount of effort to do the real to sim well with high fidelity to the real world. And then on top of that, the simulation engine are still not the same as the real world, be it physics, be it some of the, let's say, the deformable object things. So it's like, both have very, very different trade-off, it seems to me. It seems that both sucks in their own ways.
That's true. Yeah, maybe even we like use some other simulators instead of ManyScale to do the deformable objects modeling.
Okay, cool. Yeah, I guess maybe as a final question, we always ask like, are there any recent papers that you've come across recently that you thought was very interesting, you want to give a shout out to? Doesn't have to be like simulation, could be anything.
I think since we are talking about GSWorld, I would like pick some papers related to this topic. And the first one is from NVIDIA, as you can see from Tairan, the sim-to-real reinforcement learning transfer. Yeah. I think he really did a lot of efforts into this paper.
Is it called viral? Cool. I think so. Yeah,
it's viral.
Yes, that's right.
The resources is very expensive.
That's true.
Yes,
that's also the resources.
GPUs. Yeah, and also a bunch of randomizations. But here, if we use GSWorld, we only want to first reconstruct the scene. Everything. Yeah, you can. The scene is exactly the same, so the gap is much smaller. But for the viral, you have to do a lot of randomizations to enlarge the simulation distribution to make it work in the real world. And another interesting one is from Columbia, the real to sim evaluation, which do the some similar idea with our visual benchmarking here. And they are focusing on the deformable objects. And they show that simulation and real world evaluations have high correlations. and we are saying the same thing, is that
Mm.
evaluating the simulation is much cheaper. And in the meantime, it can show the performance, indicates the policy performance in the real world. So if we want to do some development and want to quickly iterate, simulation is a good choice.
Yeah. That's another good paper. Real to sim robot policy eval.
Yeah, exactly.
Yeah, guys are Cine X. I think that they have a company. But yeah, from Colombia as well. Cool, really cool. Well, yeah, thank you so much for coming on the pod, Guangqi. I thought this was really cool. Yeah, I think we'd love to see more, work like this to really stretch the capability of simulation because no one likes collecting data in the real world and having robots breaking in the real world. So we can get a lot more things done in sim. I think that's always helpful.
Real to sim is so incredibly important. It's such a great thing to be working on because building simulators also kind of sucks. I don't know.
Yeah, exactly.
Yeah,
I think both both are hard ways, and there's still a long way to go. Thank you for your kind words, my friend Chris.
Yeah. Okay. Cool. Well, we'll see you next time. Bye.
Yeah, bye.